Hey there, my name's Alejandro, and welcome back for day 197 of me doing the Daily LeetCode Challenge that I reach 1 year's worth of green contributions here on GitHub. So today's problem is for January 29th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode Medium, problem 684, redundant connection. And okay, let me, reset that. Okay, seems like we solved this before. When did we solve this? Jan 10, 2025. Oh, is this one of is this one of the Nico 150 problems? What topic would this be? Redundant correction, an undirected graph. Okay, is it a graphs problem? Max area, clone, walls, gates, routing, specifics, surrounding region, course schedule. Ah, okay, there it is. Okay, so it's a Nico 150 problem. Okay. So we saw. Okay, well, that's a little bit exposing, but okay. Yeah, okay, that makes sense. So this is one of the Nico 150 problems that I solved around 2 to 3 weeks ago, I guess. Just because I pre-record my the Nico 150 challenge videos and so on, just because I know that it will take me longer to do the hards than it will to do, like, the easies and mediums. So that way, when I get to the hards and so on, I have a bit more time than, like, the 3 per week that I wanted to do. But honestly, I might have gone, like, too highly on pace, but it's a convenient side effect. Okay, so I remember. Well, okay, maybe if I read the problem, I'll remember the problem and I'll remember how I solved it, but. Nevertheless, for now, let's just reread what the problem is, because I have indeed forgotten. So, okay, problem 684, redundant connection. In this problem, a tree is an undirected graph that is connected and has no cycles. You're given a graph that started as a tree with n nodes labeled from 1 to n, with one additional edge added. The added edge has 2 different vertices chosen from 1 to n, and was not an edge that already existed. The graph is represented as an array of edges of length n, where edges of I is equal to AI, BI, indicates that there is an edge between nodes AI and BI in the graph. Return an edge that can be removed so that the resulting graph is a tree of the n nodes. If there are multiple answers, return the answer that occurs in the last input. Oh yeah, I remember having a super efficient solution to this, but now I don't remember what I did. That occurs last in the input, right? So I remember I did something. Okay, I remember I did something where it's like I went through the edges backwards. Okay. Right, because I have to. That occurs last in the input, right? Well, one very easy way would be just like remove an edge, then run a DFS from literally any node and see if you have just one connected component. And if you do, then we're chilling, right? Here, I guess you could have removed any one. Yeah, but like if you remove this, then you might now have a. Oh, and I remember where it was like, if I did it in a specific order, or if I didn't just choose a random node, like it would actually affect my complexity. I think I did do that, right? Oh, and n is 1,000, so you can do n squared. Okay. Well, that pretty much tells it. Okay, so that's why I was able to do this problem. Nice. Yeah, because the obvious are, well, what's the amount of edges? Is the amount of edges n squared? No. Okay, it's equal to n. Okay. Then this is definitely so. You can go through every single one of the n nodes, and for each one, or well, you can go through all the edges of which there are n, right? And then it's like, you can do the case where you move it, but then it's like given the rest of the nodes, like just pick any random node and see if you can do a full graph traversal from that node, right? Oh yeah, and what I did is like if I remove an edge from U to V, I just greedily looked at between U and V, which one has like less neighbors, and try to do a search from there, and it just happened to be lucky with the test cases and so on. But the worst case, you just pick a random node because you don't know which one to pick, and you just do a DFS from there and see if there's only one connected component or not. And you know if there's a connected component or not because you just do a DFS from a node and see, was I able to reach all n nodes in the graph, right? Where here we'll define n is equal to length of edges, and keep going. Okay, so the very first thing we need to do is build an adjacency list. Here are the nodes are labeled 1 to n. So here we could just do this. Here we'll say an empty list for this in range n plus 1, right? Because if n, since nodes labeled 1 to n. There we go. Instead of using a hash map, right? Here we'll say for u comma v in edges, we'll say adjacency list. So it edge between no AI. Oh, it's undirected, right? Okay, so adjacency list of u dot append v and adjacency list. Actually, we'll need to be able to remove edges, right? So we should make these sets. So here we'll make this add v adjacent v dot add u, right? And then here we'll say for edge, well, we need to do like backwards edges, right? So for edge and reversed edges, right? Or otherwise I can do like, you know, for edge index in range n -1, -1, -1 as yeah. Well, for now we can just keep it clean this way, and to do maybe looping over indices is faster, right? But that way it's like, you know, because here they tell us if there are multiple answers, return the answer that occurs less than the input. So we might as well go through all the reverse edges and go through all the edges in reverse order and find the very first one that we can remove, right? Idea, yeah. Idea, go through all the edges order, answers, problem statement says to return that occurs input. Then for each considered edge, delete that edge and check if the graph is still just one connected component. We can even say one strongly connected component since everything is undirected via a simple DFS starting from any node. Whoops. Since the graph is undirected. If it didn't work, add it back and try with the next one until a valid one is found. Until a redundant, a valid / redundant one is found. There we go. Okay, that's kind of the idea. Step 1, build an adjacency list, sets to allow O1 edge deletion and insertion. There we go. And now for each edge, step 2, loop through edges in backward order until one is found. There we go. And now we'll say, okay, first delete the edge, add the edge. Adjacency list of u dot remove. We'll say u comma v equals edge. Or here we'll just say for u comma v that remove v, and we use v remove and not discard just to assure that they're there. That remove u. Here we'll say run DFS from any node. Check if can reach every other node, which would mean redundant. To do, don't make this random / fixed. Be greedy. Here it won't affect anything on the asymptotic complexity. For now, we'll just pick a random node. So they're labeled from 1 to n, right? So here we'll say random node is equal to 1, right? Let's just be lazy. We'll call it node. There you go. We can just do it from any node. And here we'll say, okay, stack is equal to node Here we'll have a visited set, right? And it's like, okay, while length of stack is greater than 0, here we'll have node. Here we'll say, here we can call this random node is equal to stack.pop. Then we'll say for nay in adjacency list of node. Here we'll say if nay in visited, continue. Otherwise, here we'll do visited.add neighbor node. And here we'll say stack.append the neighbor node. Right? And then that's pretty much it. If length of visited equals n, then return, what do we want to return? The edge itself? Yeah, okay. Return u comma v, right? So it wasn't redundant. Here I'll say adjacency list of u dot add v, adjacency list of v dot add u, right? And are we guaranteed a solution? Or okay, wait, no. It's since it's undirected and there's n edges, is it guaranteed that the graph is connected in the first place? I guess so, right? It's kind of like the hard that we did. Yeah. So it's just guaranteed that there is a solution. They won't tell it to us, but it is guaranteed by the specifications of the problem. Makes sense. Raise exception, unreachable code. There must be a solution. Okay, we can run something like this and see if it works. Okay, it works like a charm. Accepted. Let's submit that bad boy. And there we go. Completion streak 187 days. Consistency is key. See ya tomorrow. Okay, it kind of helps that I just saw this problem over here in the LeetCode 150 like 2 to 3 weeks ago. But yeah, okay, it's good. It's just, you know, a little test of my understanding, right? But yeah, okay. And here, this is the point where we can make some random optimization, right? Here we could do random.randint. So they're all from 1 to n, right? So this I can do as well. Right? And now I can submit and see, like, you know, does it make my things, like, you know, better? Not really. I mean, I guess it takes time for the random.randint, right? Just like by fixing it at 1, it makes things, okay? But here what I'll do is, like, let's say, what if we make it always u, right? If I make it always u, is it better? It's a little bit better. What if I make it always v? Is it always better? All right, how about u if length of adjacency list of u less than length of adjacency list of v, else v. I remember doing something like this in my LeetCode 150 video, and it ended up making things faster. Is it faster here? Yeah, see, a little bit of greed. Okay, this does absolutely nothing for the asymptotic complexity and so on. If it makes things faster, it's only because of how the test cases are, right? It's just like, you know, trying to be greedy. It's like, you might as well, you're gonna delete an edge between u and v and so on. You might as well just be like, okay, which one has like fewer neighbors initially? You know, I might be able to reach a dead end faster, right? Because I just deleted an edge from u and v. So if there's going to be, like, for example, here, if I'm able to, like, you know, delete this edge over here, right? And this guy has less neighbors than this guy over here. So obviously when I try to expand from 5, I'm going to realize, like, oh, shoot, this is the only guy I have left. And it's going to be like, okay, I have a length 1 component. And it's like, okay, well, that means we just, this edge didn't work, right? Versus if I did 1, it's like, oh, I have to look at this and this and this and this. And be like, oh my gosh, I have every node except 1 and so on. So you might as well be a little bit greedy and just pick the one that, like, you know, has fewer neighbors initially. Again, worst case, you always pick the bad one, right? Like, you know, maybe it's like, you know, 5 ends up having, like, you know, 1 neighbor and 1 has 2 neighbors, but they're both like terminal nodes, and this guy has a neighbor only 1, and it happens to be like an infinitely long chain, and you're like, oh my gosh. So at the end of the day, like, you know, in terms of asymptotic complexity, doesn't matter what node you pick. you can pick one and so on and that. This is just me, like, put a little bit of greed into the problem, so that way it's like, if it is not a redundant edge, which I'm guessing is going to be a lot of the times the case with a lot of these test cases, that it's like, I gotta put a little bit of sauce on it, always pick the one with less neighbors, inject a little bit of greed in there. So yeah, but otherwise, like, you can totally just ignore this and put something like 1. Okay, another thing I want to do is in edges, maybe backwards. Is this better? I won't enumerate it, but that way I'll just, since I have to loop through it completely anyways, right? I guess it doesn't matter, right? For I in range n minus 1, negative 1, negative 1, u comma v equals edges of I. Is that better? Not really. Dank. Maybe we do a little bit of a lesson recall in there, Maybe U's are better. No, they're not. Okay. So yeah, okay. Doesn't really matter, right? 1, delete the edge, 2, run. 3. There we go. Yeah, for here we might as well do for u comma v in reversed edges, right? I assume that, like, this enumerates it. It's sufficient enough. We leave it to, like, a Python library. Or maybe it's not so efficient. Maybe for I in range n minus 1, negative 1, negative 1 was indeed the most efficient thing, Who knows? It would just be very, very nice to get to that 0 ms. I crave it very. Hey, there we go. We got the 0 ms. There we go. Easy peasy. Not even close. Lemon squeezy. All right, nice. Noise. Okay. So as always in all my videos, I do a quick recap of I both solve the problem. So for this one, essentially it was a bit simpler for me just because I happened to solve this problem as one of the Nico 150 problems around 3 weeks ago. Back in January 10th, I believe is what I saw. And today's January 29th for the video. And which, by the way, is for my Nico 150 challenge, but the video for that is not yet released. It's just been pre-recorded. But essentially, the way that I saw this problem is in the most naive way possible, right? I recognize that the number of edges is equal to n, and that n is at most 1,000. And if you don't know, so 1,000 is 10 to the 3, and in LeetCode, you can usually get away with 10 to the 6 or / up to 10 to the 7 iterations, right? And so given that n is 10 to the 3rd, we can write an O of n squared solution and it'll be accepted by LeetCode, right? And the very first thing that comes to mind is essentially you want to figure out, is an edge redundant, right? And inside of this graph, it's undirected, right? And there are n edges, right? To make it a minimum spanning tree, basically, you need n minus 1 edges. And if you have n minus 1 unique edges, then it must form an MST, right? So whatever is the nth edge, it must be a redundant connection, which is why I have this raise exception at the very end, because I know that if there are n edges in an undirected graph with n nodes, there must be at least, one quote-unquote redundant edge, right? With just n minus 1 edges, I can already claim the fact that you essentially have a strongly connected component of a graph. It's just with an nth edge, doesn't matter where I put it, it just makes things more redundant for no reason at all, right? Because here's like, for example, no matter where I delete this edge, right, I will always have a, no, but here, did I just falsify my claim? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? If I just had 4 edges here, then this guy wasn't necessarily connected. I see. I guess it only takes n minus 1 edges to form an MST. It's just that here, if you redundantly put yourself in a connected component, so okay, I guess I got lucky with this. I actually just disproved myself there, so that's my bad. I'm guessing it's just that the problem kind of guarantees that there's always a solution, right? Right, because here I could have not put this edge. I could have put the edge from like with a 2 and 4, right? I guess you just gotta kind of assume that there is a redundant edge. Okay, yeah, you get lucky sometimes, right? But essentially, the point is like, okay, assume that you have something, a graph that's strongly connected, and there is one redundant edge given you by the problem. You want to find that redundant edge, right? And if there's multiple answers, then return the one that occurs less in the input. So first of all, the very first thing that to realize is like, okay, I'm going to go through the input backwards, right? I'm going to loop through the indices of the edges array in backwards order from n-1 all the way up to 0 inclusive, so up to -1 non-inclusive, and going backwards with that -1, right? Where n is my length of edges, and then keep grabbing that edge, right? And for each edge, I'll ask myself, is it redundant? And if so, I'll return that edge right over here, right? And the way that I do this is very simple. I'm going to go through the edges backwards. What I'm going to do is I'm going to delete that edge from the graph and ask myself, is the graph one strongly connected component? If it is, then that edge must have been redundant. If it isn't, then that means, okay, that edge was indeed necessary because removing that edge disconnects the graph, right? For example, here, if I remove this edge over here, all of a sudden it's like, okay, we have these 4 nodes in one component and this one node in its own component, right? We don't have one more component, just a singular component for the entire graph. This edge could not have been a redundant edge, right? But any other edge over here is indeed a redundant edge, right? So that's kind of the point. And so the trivial way to do this is like, okay, I want to see if removing an edge, essentially, I want to check, do I still only have one component or not, right? And the easiest way to do it is essentially like, okay, since the graph is undirected, I might as well pick literally any node, right? And just run a DFS from that node and ask myself, was I able to reach all n nodes, right? Because if I was able to reach all n nodes from a certain node, then that means it's like, okay, I have one strongly connected component for the entire graph. I was able to reach every node from one singular node. Since the graph is undirected, every node reaches every other node. It's a strongly connected component, right? Otherwise, if you cannot reach all n nodes, that means it's like, okay, you must have at least 2 components in the graph. It is not strongly connected. That means the edge you removed is not redundant, right? So literally all I do is step 1 is I build an adjacency list, right? So here I'll have, a set for well, here I do an array up to a range of n+1. You can make it a hash map, which is what I traditionally do for adjacency lists. Here I just noticed that since the nodes are labeled 1 to n, I might as well use the index as like the key instead of having a hash map where it's like, okay, the values are gonna be from 1 to n. Here I'll just have like, n+1 elements, so that index 0 basically I'll never use, but that way every node like value, including n itself, will have its own index inside of adjacency list, right? And then for every edge and edges, I'll add that edge inside my adjacency list, right? So it's like, okay, V is one of U's neighbors and U is one of V's neighbors, right? That's the point, since it's undirected, right? Now once I have my adjacency list, I'm just going to loop 3 edges backwards, right? For n range n-1, -1, -1, uv is equal to my edge. And then I'm essentially going to do this. First, I'm going to delete the edge, right? After I've deleted the edge, I want to ask myself, am I still one strongly connected component, right? And the way I can do that is I can pick literally any random node, and I'll prove this because if I do literally like random.randint between 1 and n, right? And here I run this, you'll see like, hey, this is still an accepted solution, right? So the point is I can run a DFS from literally any node that I want. I can make it 1 because I know that the nodes are always from 1 to n where there's at least one node and so on. You can do any node you absolutely want. Here I'm like, okay, might as well put a little bit of greed in there and just pick the one between u and v, which are where I deleted an edge, and be like, okay, whichever one has fewer neighbors, right? The reason this is greedy, again, in terms of asymptotic complexity, this does nothing, right? The only reason I do it this way is because it's like, okay, think about a case like this where it's like, okay, you just deleted this edge, right? If you're going to have like, an edge not be redundant, then it's likely that it's split, the u and v into its 2 separate components, right? And so really you'd want to explore like, u or v in terms of whichever one has the smallest component, right? And you can't really know that, right? The point is you need a DFS to figure out if there's one component or not in the first place, right? So it's like you might as well be greedy and be like, okay, between my u and v, I'll look at the one that has fewer initial neighbors, right? Even though it might have like, let's say U has 1 neighbor, but it has like a chain of 10 billion nodes, and V has 2 neighbors, and those are the only neighbors it can reach. And it's like, yeah, okay, unlucky case, right? But I'm like, okay, if I'm gonna pick one, I can quickly look at the length of their direct neighbors, and I might as well just like, pick the one that has fewer initial neighbors. Maybe I get lucky, right? Either case, I could just pick any random node, so I might as well be like, why not? Like, let's just pick, whichever one between U and V that I'm deleting an edge between, whichever one has fewer direct neighbors, right? And that's kind of how I get that 0 MS beats 100%. because it's likely in cases like these where it's like, okay, if I'm gonna delete an edge right somewhere, it's likely that, like, you know, if I have one strongly connected component, then doesn't matter what node I picked in the end of the day. But if I do split things, right? For example, here if I pick this edge and I did split things, then it's like, okay, we can immediately recognize that, like, you know, if I chose this 5, it's like I can immediately say, hey, there's a connected component of one node in here, which is not like, you know, the 5 nodes that are in this graph. Therefore, this was not a redundant edge, and I could have ignored looping through these 4 nodes, right? But again, in terms of worst case, there'll always be a case where it's like, you know, picking U and V was like disadvantageous, blah, 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 blah. Right? Like, for example, it's like, you know, let's say that like 5 had, I don't know, like more neighbors somehow. And so this had, like, you know, more chain neighbors and so on. So you could have gotten unlucky anyways because you're just looking at direct neighbors and so on. You need like some more accurate information, right? The point is that this sometimes helps make things faster, and it does in terms of the cases that are given for this problem. But here's like, you can pick literally any node you want between 1 and n, and it will not affect the worst case complexity, right? But otherwise, once you picked your random node, this is just how I like pick it. Just inject a little bit of greed in there. Here's just like, let's perform the DFS, right? So add our visited set with the random node that we picked, start off our stack with the random node, and it's like, okay, while there's still stuff to visit, let's pop this top of the node at the top of the stack, and then we'll say, okay, for each neighbor that is adjacent to this node that we just popped, okay, if it's been visited already, let's ignore it, you know, let's not go into an infinite loop right now. So it's like only visit unvisited neighbors, and it's like, okay, if it's not been visited, then it's like, okay, well, mark it visited because we're about to add it to our stack, and add it to our stack, and that'll be the very next thing that we visit, right? And we keep looping through this on and on and on and on until we've reached every single possible node that we could reach from the initial random node. And then what we ask ourselves is like, okay, visited will essentially be a set of all the nodes we were able to visit through our traversal starting from random node, right? So there's only 3 possible cases. Case 1 is that the number of nodes that we visited is n, which is the total number of nodes, right? The number of edges is the number of nodes in this problem. If that is the case, we have one strongly connected component, which means that the edge we just deleted did not affect anything. We still have one strongly connected component. So if the length of visited is n, we were still able to reach all n nodes. That means we have a strongly connected component. Deleting this edge was okay because it was a redundant edge. So we'll return that edge that we deleted because it happened to be redundant, right? Otherwise, if it's not n, then that means it's like, okay, since we have a connected component that we just found that is of size less than n, there must be at least one more component, maybe more than one, but at least one more component for the remaining however many n minus number of nodes we just found number of nodes, right? Right, like if we found, you know, m less than n nodes, that's like, you know, there's n minus m nodes left that might be in one or more components, right? But the point is that there's at least one more component somewhere with non-zero amount of nodes, right? So if length of visited is not equal to n, then it's like, okay, this was not a redundant edge, so let's add the edge back into our adjacency list and keep looping through our edges array until we do find a redundant edge, right? That is kind of the point. And here, just being a little cheeky and putting a arrays exception at the bottom, I realized that just because a graph has n edges doesn't necessarily mean they're strongly connected, right? For example, here it's like, you know, you could have removed this edge and put it over here, right? And then it's like you have two connected components inside the graph, even though you have n edges and n nodes, right? It's just that here, because the problem is like about finding a redundant connection, they give you an undirected graph that is connected, and I guess has no cycles. Interesting. You must have a cycle if it's undirected, but I guess, okay, I understand what they mean, right? It's like if you thought of them as like directed edges, it's like, yeah, you'll be fine. Okay, you can visit everything from a singular point, right? I guess that goes in hand in terms of why you can just pick a random node here to do your DFS, right? But yeah, so they give you the problem in such a way where it's like, okay, you basically like are kind of guaranteed to find like they literally tell you that the graph is connected with no cycles, and then that, you know, the point of the problem is like, you know, find a redundant connection. So they're going to give you test cases where it's like you have a redundant connection, you want to find it, right? Because that's kind of what the LeetCode problem is asking you to do, right? So just gotta bear that in mind. But otherwise, that is pretty much it in terms of literally how I solve this problem, right? Very, very, very naive brute force, but just happens to work. I just, like, you know, quickly check the constraints here, and I'm like, okay, like the very first like brute force idea is like essentially like, okay, go through the edges, delete them, run a DFS, and see if you still have one connected component. Okay, if I did so, that would mean I need to do a DFS from every single node, right? Well, here since the length of edges is equal to n, then that means it's like or for every edge, since the number of edges is equal to n, that means it's like I need to run my for loop n times. A DFS will take at most O of n time, which means n times O of n is O of n squared time. Oh, okay, it would be like 1,000 squared, which is 10 to the 6, which is exactly what LeetCode allows you to submit. So it's like, okay, great, let's code that solution up, put a little bit of O1 optimizations, like making the adjacency list an array, doing this little greedy thing and so on, blah, blah, blah. And that is how we're able to earn our beautiful, sexy 0 MS beats 100% solution right over here. And, hopefully that solution makes sense. Again, as a quick recap, basically just build your adjacency list, loop through the edges in backwards order, because if there's ties, they tell you to essentially grab the one that happened last in the input. And that's like for each one, delete the edge, run a DFS from any node, see if you still have one strongly connected component with n nodes. If you do, that means that edge was redundant and remove it, right? Otherwise, if it was not, then it's like, okay, that edge didn't, that edge was indeed needed to keep the graph as one connected component, so add it back in there, and just keep trying with the next edge in backwards order in edges and so on, until you found an edge that is redundant, in which case you'll just return that, right? And that's pretty much the intuition in terms of how I was able to solve that problem. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.